right, so this is one of the most difficult sections now of the two. So keep an open mind, pay attention, don't space out. I tried to break it into a couple different sections. That's why there's a part 1, part 2. Last year I just did it all together, and I think it's easier to separate it. So, all right, so find the domain of each rational function. So remember, domain is all the x values that you can possibly have. So what is the one x value that you cannot have in number 1? 0. So that means that the domain, you can just say all real numbers except 0. X equals 0. All right, you could also write that in interval notation. So if you were going to write it in interval notation, it'd be negative infinity to 0, parenthesis, union 0 to infinity. So you'd skip over the 0, right? There's no brackets there. Okay, personally, I think it's easier to just say all real numbers except this and this, you know. All right, so number 2. So looking at this denominator, I would have x minus 1 and x plus 4 when it factors. So what's my domain for this one?
1 and negative 1.
Okay, it's everything but 1 and negative 1, right? So domain, all real numbers except x equals 1 and, oh, I said negative 1, didn't I? X equals negative 4. So x equals 1 and x equals negative 4. All right, so that leads to what we call a vertical asymptote. So you guys did that graphing activity already, so I think you guys kind of know what an asymptote is. A vertical asymptote is an invisible line that you get really close to, but you don't touch. So it's going to get closer and closer to that line, and it's vertical. Okay, so that would be x equals some number, a. Okay, a is not in the domain of the function, so it's what made your denominator equal to 0. So in this first one, I have 3x over 2x plus 5. So I want to find when the denominator is equal to 0. So I'm going to say 2x plus 5 equals 0, and I solve it out. So I get x equals negative 5 over 2, or negative 2.5, right? Okay, that's your vertical asymptote. So it's a line at negative 2.5 that you're going to get really close to, but you're never going to cross. So I don't know exactly how this one goes, but let's say it does something like that, and then something like that. Okay, so there are never any points along that line. Now what makes it hard is some of your calculators actually draw in the asymptotes, which makes it really hard when you're graphing these, because you're like, wait, is that part of my curve or no? Remember, vertical lines are never going to be part of a function. So if you have a vertical line, it's an asymptote that your calculator's drawing. All right, horizontal asymptotes. Okay, there's a shortcut method for this one. So the line y equals b is a horizontal asymptote if the ends of the graph get close to the line but don't cross the line. So notice how I said ends, that's really important. So you can cross it in the middle, but not on the ends. So you might have something that crosses in the middle, but then on the ends of the graph it gets really close to that line, like that. Okay, so like I said, there's a shortcut and there's a long way. The long way is really more like pre-calculus or calculus. So I'm just going to teach you the shortcut method. You won't even learn the long way. Okay, it's really pretty easy shortcut. You look at your rational function, so the fractional expression, and you look for the largest degree. So in this case, in number 1, what's my largest power? 2. So I have something that has 10x squared and I have something that has 5x squared. Okay, you ignore everything else. Okay, you just do 10x squared divided by 5x squared. The x squareds go away. Right, they cancel out. 10 over 5 is just 2. Okay, that's what the line, remember a horizontal line is y equals. So it's the line y equals 2. And that's it. That's your horizontal asymptote. Yeah, turn. It can cross in the middle, yeah. Yeah, these ones would, it looks like there's vertical asymptotes maybe there. But the horizontal one is the one I want you to really see. Yeah, Taylor.
Are there going to be ones where it's just like 10x squared and like there's nothing in the denominator?
Yep, so let's look at this next
like
one.
that,
Okay, we're getting there. You're one step ahead. All right, so if I have 2x squared plus 50 over 4x cubed minus x minus 1. So what's the largest power? 4x cubed, right, the cubed. Now there is no x cubed on the top. So once we find what the largest power is, if there was nothing in the other location, write 0x cubed. Because there was no x cubed term. So that means we'd have 0x cubed over 4x cubed. So what's 0 over 4? 0. So y equals 0 is the horizontal asymptote. Okay, so now Taylor was asking about the next one. She was saying, well, what if there's the highest degrees on the top and there's nothing in the bottom? So see how you have 2x to the fifth, but there was no x to the fifth on the bottom. Okay, well, let's write 0x to the fifth down there. So now we have 2x to the fifth over 0x to the fifth. So what's 2 over 0? Yeah, it's undefined. So what do you think that means about our horizontal asymptotes? There isn't one. Yeah, there's not one. So no horizontal asymptote. Okay, occasionally you'll have something called a slant or oblique asymptote. So these are asymptotes that look like just slanted lines. So it might go along something like that, along this slant. When this happens, the degree in the numerator is always exactly one more than the degree in the denominator. So see how you have degree 2 on the top and degree 1 on the bottom. Okay, that means it might have this slant asymptote. Now notice how I said it might. If it factors, so see how the top factors? If it canceled with the bottom, that may eliminate that slant asymptote. Do you guys see what I'm saying? So if you factor the top and it removes that x minus 3 on the bottom, then there's no slant asymptote. Okay, but in this case, if you factor the top, nothing is in common with the bottom. So there is a slant asymptote in this one. Okay, and we'll do some more where you'll see that. Okay, so you can find the slant asymptote with long division. So this is the part that people don't like, but hopefully you guys remember your long division. So we take our x squared plus 5x plus 4, and you're going to divide by the bottom, x minus 3. So remember how we do long division. I'm going to say, what do I multiply x by in order to get x squared? X. I write that on top. So then I say x times the whole divisor, so x times x minus 3 gives me x squared minus 3x. Draw the line, change the signs, right? Because we're really subtracting, so we've changed the signs. The x squareds go away, you get 8x plus 4. You repeat. So you say, what do you multiply x by in order to get 8x? So you need plus 8. Take the 8 times everything in the divisor, so 8 times x minus 3 is 8x minus 24. Draw the line, change signs, you get 28. That's your remainder. That part doesn't matter. I mean, it's basically like you have, oops, I don't know what just happened there. It's like you have plus the remainder out of that divisor, x minus 3 left. Okay, we're not worried about that though. The only thing we're worried about is the quotient, x plus 8. That is our slant asymptote. So it's y equals x plus 8. so really not too bad. If you guys remember long division, it shouldn't be too bad. Okay, so basically if I wanted to draw that slant asymptote, you'd draw that line. You'd go up 8 for your y-intercept, draw your point, slope is 1. So it'd be that line right there. Okay, we'll talk more about graphing. Okay, so holes. So this is a case where it looks like you might have a slant asymptote when you look at the degrees, because you're like, oh, this is degree 2, and this is degree 1. Does it have a slant? And the answer is no. Because what happens is when you factor the top and the bottom, x plus 2, x minus 2, over x minus 2, the x minus 2's cancel. So you no longer have a rational function in the end anyway. So you just get x plus 2. Okay, this is the function that we're going to graph. We're going to graph this simplest form, y equals x plus 2. So if I have y equals x plus 2, that has a y-intercept of 2 and a slope of 1. So you're going to go up 1, right 1, up 1, right 1. Okay, so that's my answer, almost. Now think about if you made a t-table for the original. If you made a t-table for the original, what can you not put in for x? Close, not -2, but 2, right? If you put 2 in, it's undefined. But right now, the way I've drawn it, it looks like at 2, we're at the point 4, right? It looks like at 2, 4, we have a point. So what do you think we have to do at 2, 4? Not curve it. Skip it. Yep, that's exactly it. So there's just a hole there. You just skip over that point because it's not in your final answer. If you had done a t-table from the beginning, you would have gotten all these points. I mean, you could do other points like 0, 1. If I plug in 0 into my original, you end up getting 2. If I plug in 1 into the original, I end up getting 3. You would get all these points. So all these other points, but you would not get a point at 2. Does that make sense? Okay, so let's try another one. Okay, so I'm going to factor the top and the bottom. Okay, this is another one that simplifies at the very beginning. So when that happens, when you have something cancel on the top and the bottom, that means there's a hole there. So there's a hole at whatever made that 0. So a hole at x equals 3. So that's how that last one was. When we had this that canceled, we know that there's going to be a hole at x equals 2. That's equals. Okay, so I know I'm going to have a hole at 3. I'm going to graph the simpler function. I'm going to graph 1 over x minus 2. Is there a vertical asymptote on this one? Is there a horizontal? Remember, vertical asymptotes were when the denominator equals 0. So does the denominator equal 0 in this case? Ever?
At 2.
Yeah, at 2. At x equals 2. What about 3? It wasn't the original, but remember that's a hole. So since you canceled that out, that's no longer a vertical asymptote. So no longer a vertical asymptote. Okay, the horizontal asymptotes. So remember, you do your trick. I always say, ha, there's a shortcut, ha, H-A. Ha, there's a shortcut. That's how you remember that's the shortcut method. You guys don't think I'm funny at all. That's okay. So if we're doing this one, it's y equals. Our largest degree was 1, right, x to the first. There was no x to the first up here, so it's like 0x over 1x. So it's 0 over 1, which is 0. So y equals 0 is the horizontal. So if you're graphing it at y equals 0, you have a horizontal asymptote. At x equals 2, you have a vertical asymptote. At 3, we're not going to have a point. At 3, it's going to be a hole. But you can try some other points if you want to see what happens. So let's say I want to see what happens at 0. So if I plug in x equals 0, what number do I get into this simpler function here? Close. -1/2, right? So I'm crossing right here. Now remember, on the ends, you're going to go along that horizontal, and you're never going to cross that vertical. So just knowing that one point, I know what half of my graph looks like. Can you guys see it? It's going to go along this horizontal, and then it's going to come along this vertical, like that. Now I want to know a point on this other side. So let's say I plug in 4. If I plug in 4, I get 1 over 4 minus 2, so 1/2. So it's like right there. So this is going to come in along the vertical and then along the horizontal. And then your very last step is to remember that you have that hole at 3, which sometimes people will forget. Remember, at 3, you're going to have an open circle there. And that's what your graph would look like. All right, so steps for graphing. We're just going to go through those different steps. Yeah? All right, we'll do that tomorrow, though.